Okay, so welcome to the fifth presentation of this seminar series on cognitive robotics offered by QMUL University of London. And today I'm extremely happy to have Angelo Cangelosi, Professor Angelo Cangelosi, with us from the University of Manchester. He is one of the most prominent figures in developmental robotics, and as witnessed by also by this first initial slide that is the cover of his book. And master students at QMUL, they should know this very well because it's part of their teaching materials. But of course, Angelo is very popular in the community of robotics, and especially cognitive robotics and developmental robotics. And I particularly like of his research that I think is really a manifesto for the research on cognitive robotics, because he's applying specific psychology experiment, is reproducing specific psychology experiments with robots to see how computational models can match the human behavior. So his research is really into using robots to explain human intelligence and also achieving some advanced capabilities with robots. So I think it's amazing, and I'm looking forward to the presentation. And I'll just shut up now and leave the floor to Angelo.
Thank you, Lorenzo. Thanks for the invitation. And I would like to add that it's nice to see that the new generation of researchers in the field of robotics and cognitive robotics, Lorenzo is one of those. He used to be a postdoc at the time we were working on the my iTalk project with the IIT. So it's nice to see this now a professor in our community. So as Lorenzo explained, the approach that I take is a distinctive flair, I would say, where we have a more closely defined link between cognitive robotics and cognitive psychology or cognitive sciences. So in some approaches in cognitive robotics, you loosely say, oh, I want to model the way children learn to speak, and then you just build your own machinery. You will see in our experiments, any robot experiment is actually constrained with a task, with some developmental stages, to phenomena that we know exists in development. So I would say this is what will make it a bit more distinctive. In fact, I have two main aims in my research. One is to design, as a computer scientist, an AI person, to design the software for the robot. So if you want the intelligent component of robot control, in particular, I specialize on communication, language, and speech. But in addition, because of my close interest to psychology and my actual training in psychology, formerly I used to be, I say, a psychologist and experimental psychologist, we use sometimes our models, cognitive models, computational models in robots, to also understand better what happens in humans. So it's a two-way process. But I would say 80% of what I do and what I will present is the first part, and then I will mention briefly at least one experiment where we predicted the behavior of children, and this was confirmed after experiments. So I said I specialize on language and communication, but language should be interpreted in the wider context. We also call it pragmatic. That is how you use language in your interaction context. So there is a famous book by Quine, a philosopher of AI and cognitive science. And Quine uses this example. Let's assume we are in the Amazon. We discover a new tribe. We don't know the language. We want to understand the meaning of the words that they use. And we hear the sound gavagai. When I, the observer, the anthropologist or the visitor, and the local people are looking at a scene like the one we see here, I don't want to describe it because I'm going to use words, and I don't want you to think of my words. So, but we have to verify the hypothesis of the meaning of gavagai. So if I ask you in a classroom, an interactive classroom, and I ask you, what's the meaning of what's the possible meaning of gavagai? Because we don't know at the beginning for sure. Most will say rabbit, some will say girls, some will say green, some will say animal, some will say pet. All of us are right, because the only way we can know the real meaning is by extending our interaction. We call this cross-situational learning. We compare learning across situations. So if I see another picture with a different type of rabbit and I say gavagai, then we might guess that gavagai means rabbit. But if I hear the sound gavagai, when I look at the picture where there is a dog, then Gavagai is not rabbit. It might be animal, it might be pet, and so on, right? So we discover the meanings of words in our interaction task via cross-situational learning and via physical embodiment. We don't go to schools when we are babies to be taught individual words. We learn words by using them in our context. In fact, Quine wasn't really talking about an hypothetical experiment. Quine is talking about something very specific. We as babies grew up in a world where we heard the word rabbit, or if you were in Italy, the word coniglio, and we have to map this word into a specific representation of an animal with long ears, fluffy ears, eating carrots, and so on. In fact, one meaning of this could be, carrot. I mean, you can barely see a carrot, or you could say, if I see a rabbit and I want to feed a rabbit, I say, has anybody got a carrot? So we can talk about words which are not necessarily there. Now, is this related to computer science and to robotics? It is related because we speak to machines, we speak to Alexa, to all these digital assistants, to our phones. So we have speech systems there. But if you have a robot that is helping you in the home to cook, for example, or to serve you, or to support an old person in the house, the robot must be able to understand the meaning of words in addition to using long sentences. So Alexa can talk to you extensively, have a dialogue, but there is no real sharing of meaning. Sharing of meaning in the context of pragmatic. What do I do with the words? Instead, with the robot, I would like to have a full pragmatic sharing, so that if I say to the robot, can you make me a cup of coffee? I expect the robot to go, make the coffee, and bring me the coffee. I don't want the robot to give me a recipe for making the coffee. Alexa will give you a recipe, right? Instead, our robots have to understand and map the words, the meaning, into their own view of the world, their own feeling of the world, their own action on the world. This is why our interest in language and robots is relevant, and you will see in a moment, this is why we looked at developmental stages. So we can easily pre-program a dictionary in a machine or the rules of a grammar, but making machines understanding things is hard. And I'll show you why it's hard. Let's assume I have my robot or my Alexa, and I ask the robot or Alexa, or a robot that uses Alexa. There are sometimes you can connect the Alexa API to the robot, right? If I ask the robot, can you tell me the meaning of push? Which for a robot should be very easy. I mean, our robots don't do too many complex things, but they can push objects, right? So the robot should know easily. And in fact, the robot using Alexa would say the meaning of push is to press forcefully against to move. If it's giving me, Alexa can only talk, right? So it's giving me an explanation. This is an explanation, which is a definition in the dictionary. Let's pretend this is the American English Webster Dictionary. And the system is, without sending words, is telling me words after words after words. In fact, if I ask to define within push, it uses the word force. For robots, they got force sensors, so force should be straightforward. The force for a robot is the state of a force sensor, if you want. But this Alexa-empowered robot will tell me force in my dictionary is defined as energy or strength. But what's energy? Energy is defined as strength of force. You see, energy defines force, and then force defines energy. Call this the merry-go-round. Stephen Harnad calls this a merry-go-round. You go back like a horse, again with a horse, to the same point, words, words. This is not good because the robot must show me what it means to push, to perform the action. Actually, it must do it, right? In addition to give me, if you want, definition. To make it relevant, not only to robots, but to people also, I'm going to talk about the Chinese room experiment. The Chinese room experiment says that if you have a non-Chinese speaker person inside a room, and this person has two things, a dictionary, like you saw before with the push, okay? Each word is a series of definitions, other words that define it. And then you have a reply rule book. It's what you see here in the middle. You have 2 pages of a book. On one side, you see the question, and then on the other side, you see the answer. This is the only thing you need to know. Look up for definitions and reply questions, answer, reply rule book. So if this person in the room is there and the real Chinese speaking person here outside writes down a question and he passes it to the room, The guy can take this question, can map symbols. The guy doesn't speak Chinese, doesn't understand any Chinese word or symbol. And then he will choose out of selection in output, he will choose a written answer to the question. And to make this real, we are going to do now live our Chinese room experiment, meaning I can see at least one, when I noticed one of the first people to join a Chinese looking name. So Chinese people, this is not for you. This is my Google Translate. I tend to translate something, so I don't really know if it means anything, if Google translated very well or not. But you have dictionary. This is a word, and this is a definition of some properties. You know, it could be apple, round, red, edible, and so on. And the reply rule book. If I ask you the question here, look at the top, very strange symbols, right? Blah, 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 blah. Questions. Then what do? You look at these questions, you go here, you map it to some parts of the structure. Here it is, right? You see first part is the same, second part is the same, only the third part changes, right? Then this is how you give the answer. You can reuse the changing bit, you have the answer, and then you need to find some other elements. Now this is the Chinese room experiment. Because we are not used to running a Chinese, to look a map and match Chinese characters, I'm going to translate this into another language. This is a real language. This is not Italian. It might look Italian, but it's not Italian. So I'm going to run a Chinese room experiment with you live. I'm going to ask you, if possible, to give me answers in the chat. So the question I'm asking you is, quanti anni avevi la picciotta? Doesn't matter the sound, this is the words. You have dictionary. So for example, you have a definition, picciotta. Picciotta is defined by 7 anni, picca appetito, mangiare ovo, and so on. And then you have a reply rule book. The question here will match one of the 3 questions there. Okay. So, and then this is the way you have to structure the answer. You substitute symbols, match symbols, substitute, look for something. I would like you to give me the answer to this question. And I'm going to give you now 1 or 2 minutes for you to try to do it. And please write down the answer in the chat box. Lorenzo can actually, in a moment, read the answers aloud to me, because if I switch to the chat, you will see this. So I can't really do this. So please try to answer the question. Don't worry if the answer is partially wrong, totally wrong. I would like you to reflect that it is possible. So, quanti anni avevi la picciotta? I need an answer from you. Lorenzo, you tell me if you see any answer appearing in the chat.
Yes.
Read this aloud. And you start to see the first answers, you can read them aloud. You should recognize the sounds. So remember, look at the question here. You match in one of the 3 reply book questions. So I'm helping you, is the first, clearly. Quanti, anni, avi, la. Picciotta is this variable x. So answer la, constant, fixed. X is, I don't have to give you the answer. X is here. And then, is there any answer?
We just got
our participants, child.
Yes, we just got 1 answer that actually I gave an answer, but before myself, someone else gave an answer, and it's the same one, which is la picciotta avevi 7 anni.
Okay, we assume this. I mean, you are cheating. It's not Italian, but as I will explain.
No, but the other person who gave the answer is definitely not Italian, I think. So
that's good. Very good. Very good. So okay. So I guess we can reveal the mystery here. So the correct answer is what you gave. La picciotta avevi 7 anni. How did you do this without looking at the meaning? Without knowing the meaning, you can't know the meaning. So you mapped X with picciotta. This was easy. I helped you. So la picciotta avevi anni. But before anni, you have another variable which I call A. So you need to guess what the A. How do you do this? You go to the dictionary, picciotta. We're talking about picciotta. So let's look at the word anni. There it is. So we do a mapping between anni and anni. And before anni, there is a word, setti. That's why I assume you answered la picciotta avevi 7 anni, which is very good. Okay. So you did a mapping of words without any knowledge of the meaning. I mean, Lorenzo cheated. One of the words, anni, is actually an Italian word. So these are the questions that I normally play with if I'm
We
recording my camera.
we had several correct answers, including answers from Chinese speakers. So it's
Okay, so
fully working.
it is possible. So what we are doing here, this is not, I call it Angelo's room. We should call it the Sicilian room experiment. So I'm speaking to you in my dialect, Sicilian, which is quite different except for a few words from Italian. For example, the first word picciotta doesn't exist at all in Italian. And you can do this. So you can speak Sicilian, like in the Chinese room experiment. If you were to answer, if whoever, the Chinese person answered correctly my question in Sicilian, I would think, oh, he or she knows Sicilian, but clearly this person doesn't know it. But let's go back to Gava guy. I'm a robot, or I'm an anthropologist, or I'm a baby that wants to understand the meaning of words because I need to use it. So if I grew up in Sicily, I need to understand the language that they use to do things with these words. So what's the meaning of picciotta? Gava guy, remember, I'll show you this picture. So if I ask you what's the meaning of picciotta, some will say, the majority will say girl, other will say person, or somebody might say young person, you know, it could be a boy or a girl. So the answer is really girl, I can tell you, in English. Okay, picciotta is girl. And just to, in Italian, the word would be ragazza, so very different. No way to guess it unless you have watched The Godfather, because there are picciotti in The Godfather in Sicilian. So it means boys or girls in this case. In Zanzina, it's if you know America, you like America pancakes and on Jemima maple syrup. This is on Jemima. So aunt, it's my aunt, let's say, Zina. This is a real story. It's okay. So Haddina, everybody will tell me chicken is not ambiguous, ovo is egg, Simenza is seed. Okay. Up to here, we are grounding, we are connecting pictures, a perception on our world, visual perception, into sound words. We ground language into our experience. 4 concrete words. Now let's consider this other word which is a bit trickier. Picca. What's picca? If I ask you, some will say 3, some will say eggs in plural, some will say many, some will say few, some will say food, right? And then if I show you this, whoever said 3 was wrong, right? Because it's actually also picca is valid for 2 seeds or 3 eggs. So picca is not the number. Picca is maybe about quantities. And if I show you this, you will tell me by cross-situational learning, contrasting situation, that picca probably means few, assai means a lot, many, right? Which is correct. Then mangiare, finally, if I show you this picture, you can guess, it might mean Mr. Bean, it might mean man, it might be to eat, it might mean pizza, whatever it is. Or if I show you a series of actions, you will guess that the word is actually the verb. It's not a description of a static element, but it's the verb. So this is to say that to ground language as babies, as Gavagai anthropologists, or as robots, I need to map the word, the sound, into my experience, visual experience, perception, and motor experience when I eat, when I do something, which is exactly what we do in our research. So instead of pre-programming a robot with an Alexa, connecting it to an Alexa, they will do all the syntax, all the grammar, all the phonetics for us. We, on the contrary, want to help the robot to grow through stages, like a baby, to discover the meaning of words. In fact, children are slow at learning words. A child which is 1.5 years of age, 18 months, knows maybe 10 words on average. But then after, at the end of the second year, children learn hundreds of words by single presentation. Also, children don't go to school, as I said, to learn the meaning of words. They discover them while they interact. They use their body. You will see the experiment in a moment. Then even if the brain has visual perception here, motor control here, Pulver-Muellers and others have demonstrated that actually these areas are co-activated when you perform linguistic tasks. And further, we don't learn in an isolated world, we learn in a social world. And to live and learn in a social world, you need to have a theory of mind of what people know about you, about the world, and so on. And we are going to look at examples of this. So the approach is called developmental robotics. I understand some of you are students of Lorenzo, so you will know it's all about modeling development. And let me do some self-promotion. You know the book, I understand. Chinese speaker in the Chinese room experiment. There is a Chinese translation, just Scientific America. This is not about my work only, it's about a few colleagues. And Japanese, of course, and I guess, Lorenzo, you mentioned the book. There will be next year a new book titled Cognitive Robotics, which I edited together with Minoru Asada, which might become the textbook for a course in cognitive robotics. It's with the publisher, MIT Press at the moment. Okay, let's now look at a series of examples. So mine is a long introduction, but I do this on purpose because I want to set the scene of the approach that I mentioned at the beginning, which is relatively distinct in my lab, where there is a very close, continuous, repeated, going back to the experiments that psychologists do with babies. In fact, if I focus on the way children use their body to learn to speak, embodied language learning, what we do, we simplify a time scale of development for what concerns language. So the first year of development here, it's all about phonetic discrimination. Children learn to tune their articulation and their perception of sounds without really having meanings. Second year of age in the middle, we subdivide into two. The first 6 months, 12 to 18 months approximately, children learn to classify the world visually into perceptual categories. So bananas have a specific shape and they're always yellow. Apples have a specific shape, but they can change color. So we recognize that. And in addition, bananas and apples are linked to a specific motor action. So the way I eat a banana, remove the skin, is different from the way I eat an apple with the skin, for example. And then second part of the first year, 18 months to 24 approximately, we have this vocabulary spurt. We start with few words. Spurt is because there is a sudden increase in performance of the number of words that you add to your dictionary. Third year of age, you speak better, you improve your language production, you start to put two words together, more milk, 2 bananas, and so on. And then you go towards complex grammatical structure. Can I have a banana, please? And so on. We do this once we identify these milestones in cognitive development for language learning in particular. We collaborate with child psychologists. For example, Linda Smith, Indiana, you will see an example. Jessica Hurst, Sussex. Caroline Floccia, Plymouth. Katie Toomey, she's now in Manchester. And Marchetti from University Cattolica Milan. And we do a series of experiments on theory of mind, on gesture, on language learning, and so on. And I'm going to show you a video from Linda Smith and Samuelson study that shows how we take direct constraints from child psychology experiments to teach our robot to speak and ground the words into their environment. I believe you don't hear the sound here, which is okay. In this specific video, Lorenzo is correct. There is no audio still, right, of the video?
Yeah, we cannot hear audio.
Okay. So what the lady is doing, the lady is interacting with the child on the other side of the table. There are two objects that the child doesn't know the name, from which the child doesn't know the name. And the lady, the researcher, never says the name of the object until you will see the object is hidden inside a bucket, meaning the object is not visible to the person. So when the child sees the object, it doesn't know the name. Now in a moment, she says, look at the Modi, look at the Modi. So you are looking at the Modi, but you don't actually see the Modi. Modi is this new word that she invented to give to, so that the children can name the object that we see on the right, this kind of game, toy. This is the Modi, okay? Artificial name. So she lets the child play the game, and then in a moment, so what she says is, can you find me the Modi? Okay. Can you find me the Modi is a test to see if the child has learned that Modi is the name of the object that appeared on our left, on the left side of the child. So let's summarize the experiment. Left, right, you hide the object, step 5. You make sure, you experimenter, that the child is paying attention with her body posture, is paying attention to the left side of the table. And then that's why they use the bucket. The bucket makes sure that on our left as babies, that we move our body towards the left instinctively, just to touch the object. So you say the word, and then you show the object, you mix them, and if you do the experiment with children, 73% of the group of children learns the body is the object on the left, which shows that it is about paying attention to left and right. And to really demonstrate this is the case, if you weaken the association between space of the object and word, you see here, the MODI object appears first on the right and then on the left, so 50% chance. No surprise, when you ask the child, what's MODI? Half will say it's this object, half will say it's the other object. So between the two, the only constant element is the fact that you keep a constant position of the object, and position is, as I insisted, postural position. It's not the child in a eye tracking setup with the chin fixed that is moving the eyes. The child is playing with the object, which is part of the task. And many, many years ago, we started to apply this, and then you will see the latest work. So I'm going to skip this video because you wouldn't hear it, but Tony is going to show the robot the object, and is going to name it and so on. There will be a video later with subtitles, which you can appreciate. So I'll skip this. So what's behind this? We are computer scientists, at least some of us. Some of you are students in this MSc AI and robotics. So what's behind this from an AI point of view? Behind this, there is a cognitive architecture, an AI architecture, which we call ERA, Epigenetics Robotics Architecture, that combines a series of Conan maps, self-organizing maps. So this is a SOM map for color representation. This is a SOM map for shape representation. This is a SOM map for postural representation. The robot maps its postures, its poses in the environment with an internal representation in a self-organizing maps. We use speech recognition system to segment individual words, and then all these SOMs are pre-trained, so that I start with a baby ICAP, baby robot, that recognizes colors in a continuum self-organizing map representation, where distance between units which are active corresponds to similarity distance. The farther away they are, the more dissimilar they are conceptually in terms of colors or shape or body posture. These are pre-trained. Instead, during the experiments, the dotted lines in the middle using Hebbian associative learning are tuned, adjusted, learned by auto-association, by associative learning. If the body posture is in the left and I see a yellow object and I see a specific shape, then I start to learn the association. Of course, at the beginning, the body link is important to learn the association, but because there are cross links between these maps, color and speech will activate their associations even when the body is not involved. So the body is important at the beginning to help create some of the associations. Later, you don't need to be in the same posture. And what we did, we ran a series of experiments. For the first 3 columns here, the first part of the charts from the paper 2015, we conducted a robot experiment, the gray data here, lighter gray, after we read a paper on their experiments. And we show that in the first case, the experiment without switch, the robot and the child learns to do the association with the MODI. The second one, because you switch the position, you don't do it. They didn't need to do it for the robot in this specific case. And then this is important here. The last 2 columns were experiments where we roboticists first created additional robot experiments and predicted that in one condition you get high performance, in the other condition you don't, below this kind of threshold. And then they in Indiana conducted some experiments, and they showed that we were right. Our robot prediction was correct. In this case, the prediction is that in addition to moving left and right, you can move also vertically the manipulation of the object and the child, so that you can learn harder tasks. You can remove interference, we say. Remember, I said at the beginning that we would like to, in addition to designing better robots that can speak and understand words when interacting with people, we also want to help psychologists to better refine hypotheses or mechanisms that link, let's say, postural change, attention via posture, to language learning at these early stages of development. What we saw was about language learning for object that you see. Here, you will see that we can also train the robot with a slightly different architecture. This uses a deep neural network. It's actually called MTRNN initially. Multiple time scale recurrent network developed by Giuntani. So here you collect a series of data, you train the robot offline, and then at the end, you look at generalization of the robot, how the robot can respond to this. First, we do motor imitation, and then we start to add labels to the objects. In fact, in this video below, so Martin says, slide left the ball. This is the linguistic instruction that the robot has to understand. Slide right the ball. Now Martin says, well, slide right the ball. And you can see the robot does it. So what we are doing here, we are extending the previous architecture to be able of understanding also actions. And now, in our field, we say that we have a vision, a wish, a dream, that I can send a robot to like a nursery school, a kindergarten, leave the robot there when I go to work, like we do with our babies. Then when I come back, the robot will tell me, oh, today I learned many things. So let's see this kind of vision. Here, you're going to see the transcript of the interaction, verbal interaction. So it's self-evident. So this mechanism is called fast mapping. When you say the name of the object and the object is visible, you say fast mapping. When Tony says this, you activate learning. When Tony says where or what, it's a test phase of your neural network architecture. This mechanism is called mutual exclusivity. If I know the name of an object, and I see a new object, and I hear a new sound, the child assumes that the name of the new object is the new sound, stapler in this case. Now we start to add two words in a sentence. So first you teach, and then the robot is answering red. Now we generalize with language. Remember, what is not is a test, so the robot knows the shape and knows the name of the shape. Here the robot knows the color, so it can only say red. And so on. And then you can continue to show the longer interaction. So we call this open-ended cumulative learning. In the same interaction, you use many mechanisms, mutual exclusivity, fast mapping, word order to teach the robot, word meanings, knowledge, linguistic knowledge, contextualized within the task, of course. You see colors, you need colors. If you remember my Sicilian room experiment, we had the concrete words, picciotta for girl, egg for ovo, and so on. And then we had more complex words, kind of abstract words. And one example of abstract words are numbers. So if I ask you, how do we teach the concept of one, two, few, many to a child, you will have to say, and remember that the way we learn to count, to understand words, is by using finger counting, by pointing an object being counted. Even in education, the frog example comes from educational material. To show concept of number series, you show that the frog is jumping and so on. You make an abstract word, number 1, 2, and 3, concrete by referring this to concrete physical or motor operations. This is what we did with our robots. We have taught robots to do finger counting, to do gesture and counting, and to look at other words. So one interesting result here, this is the counting. I focus on the finger counting example. We compare 3 robots. Robots that can only do finger sequence. So in silence, they do this with the fingers. Robots, second type of robots, that do sequence only, number sequence, words, 1, 1, 2, 1, 2, 3. And then group 3 are robots that say 1, 1, 2. So they say their sequence whilst they are moving their fingers. which is the more realistic case. Here you will see the robot performing a series of finger countings, but let's look at one interesting result here. What's the meaning of number 1, 2, and 3? If I show you one red piano, and I say 1, if I show the robot one table, if I show the robot one person, if I show the robot one group, the word 1 has no relationship to any perceptual regularity. Or if I want the robot to understand that 2 is more than 1, and 1 and 2 are similar, and 1 and 10 are very dissimilar, how do I teach this? I'm going to show you an interesting result. So we visualize here with these clustering algorithms the case of the group 3 on the left here, finger and number counted. The robots that do 1, 2, 3. Robots that do this, you see, the arch here, the longer is the step to link two numbers, the more distance semantic the more semantically different they are. The shorter the distance, like the distance between 1 and 2, 2 and 3, means that things are very similar. In fact, the robots that learn to do 1, 2, 3, 4, understand, in the sense, create an organization of their internal layers where the patterns of activations, the vectors of activations of the units are similar for numbers which are similar in sequence. So 1 is near 2, 2 is near 3. 1 is very far, you see, go up and down from 10 and from 9. So using your body helps you to structure the meaning of numbers into a continuum here, left to right. 1 to 10. Left to right, of course, in your hand. Space is in your hand. Your representation is more abstract. Instead, if we visualize here the similarity of numbers for robots that can only do the bubbling of the sequence, 1, 2, 1, 2, 3, without using the fingers, you can see here there are similarities which are not related to the numbers, but are related to the sound. So 7 and 6 are similar because they share the same sound, S sound, right? S, 7, S, 6. 2 and 10, which are very similar, share some similarity. 2, 10, 2, 10, 2, 10, okay? That's why if you allow a robot to learn to count only without using its body, you can't really order the numbers in their, let me say, mind, in their internal machine learning representation, which is related, will be very different from what's in the real world in terms of number sequence. More recently, we started to apply the same with the real ICAP. We added a convolutional network to do the real perception of a series of training data sets taken from this video. And here we show data from child psychology. Remember, we always map, not always, we tend to often map real data from children with robot data. You can see here that the worst performance in number counting is for the robots that don't use pointing, robots and children who sit at a table and count without using the fingers. Then you can have a puppet pointing at the robot, or the robot itself, like in the video. And if you do the case, children in gray and robots, ICAP in blue, you see, they improve their performance. By using finger counting or by observing a puppet that points at the object, you are learning better. This is very recent work by my former student, now postdoc, Leszek Pecina. Okay, now let me conclude. I have 5 more minutes before we go for questions on trust. I said that we want to model the robot that grounds words into its action capability, its perception capability, but we want robots to be autonomous and to learn in a social context, including not to trust, but teachers. In fact, there are some studies that look at trust and language learning. This is a project funded by the US Air Force. It's the Thrive project on trust and human-robot interaction. And we have 2 lines of research. One, we look at the robot's trust of agents. Then we look at the second dimension, human-robot interaction experiments, where we look at how humans can improve their trust of robots. But I'm presenting today the first part, building cognitive architecture for trust in robots. Remember my developmental approach, how do children develop theory of mind? How do we test theory of mind in children? Theory of mind is the capability to understand that other people have beliefs, desires, goals. Basically, they have mental states. Okay, so we want to have a robot that understands that the other people, have their own intention goals, recognize the intentions and use them for the interaction. So the way this is studied in children is with the Sally-Ann task, also called false belief experiment. It's a cartoon. So you show two characters, Sally on the left and Ann on the right, two locations. Sally has a toy, a marble, a ball. She hides this in the basket. Sally goes away. The naughty Ann swaps the location of the object when Sally is away. And then you ask the children in the final frame of this cartoon, when you have Sally returning, you say, where will Sally look for the marble? If you have younger children, 3 to 4 years of age, the children will say that Sally is going to look for the marble, for the toy, in the box on the right. Instead, if you ask all the children, 6 plus, they will say that Sally is going to look for the object in the basket, not, of course, in the box, because they know, theory of mind, that Sally doesn't know that Anne moved the object because Sally was away when Anne did this. This is a famous test. What we did, we built a Bayesian network representation of the trust and the expected behavior of people, where the child, the belief of the child, integrates probabilistically what the child knows and thinks about the location of this object and what they believe the other people, Sally, Anno, and another person, will know and think about the object. Now, we have applied this to, I don't remember if there is subtitles here, let's check. Okay, no, there are no subtitles. So this is the parent that teaches the word cup, learn cup, like in the previous example. Now you have a second person, red t-shirt, the naughty one, that says, this is a dog, okay? So the robot knows that that's a cup. Somebody is teaching it a different name, so the robot is updating its theory of mind of this red t-shirt guy as an untrustworthy person. The blue shirt girl, she says, this is a cup. So the robot confirms that she's a trustworthy person. And now these two people are going to teach the robot the name of a new object for which it doesn't know any name. So this is a llama, one name, llama. And then she says, this is a ducks. So the alternative name is llama or ducks. And because I know the trustworthiness of the person, when my parent comes back and he tells me, what is this? So what is this? The robot says, I think this is a ducks. Okay, so this shows how we link language learning experiments with trust. And then the final video is variations of the experiment the psychologists have done in San Diego Vanderbilt, where instead of having Sally and Anna telling the story, here you have a robot playing the game where you hide objects on the left and the right. This is with subtitles. It's the final video. This is collaboration with Antonio Chella, a professor in University of Palermo in Sicily. Be aware that the word trigger here is, for us viewers, the robot doesn't know this word. The robot is building a theory of mind of a trigger or a helper. Theory of mind via interaction and experience with the person. And second stage, I'm going to use the theory of mind which I built. This is the Bayesian network of the probabilities to decide what to do. And now, final element, I can map this into new people. And the last element is the belief estimation. The robot reads aloud in words the state of its decision making. So it's predicted that P left, probability for left is higher. So it is telling the person, this is why I'm trusting you, I'm not trusting you, okay? So this is, we call this explainable AI. If we have a robot that can explain its internal decision making with words, with symbol, visualizations, then the trust will improve. These are things that we are studying at the moment. So to conclude, I'm presenting theoretical and experimental approaches to cognitive robotics. Of course, we want to look at application scenarios. So areas in which we work are robot companion for older people, human joint flexible manufacturing between people and robots in, let's say, factory scenarios, and then children robot tutors. This is a collaboration with the it's work by Tony Belpame in Plymouth and now in Ghent, and then we've done work also on swarm robotics. And let me conclude by summarizing what I think are the achievements of what we have and what we should be doing for the future. So human-centered AI robotics. The approach we are proposing, keeping the person in the loop, is one advantage. That is, you try to model the same learning sequences, but also in a human-centered view of AI, you have the person in the loop. In our experiments, we followed our ethical procedure. We involve them in the design of the systems to make sure that they are acceptable. We have shown that embodiment, grounding, and social grounding in terms of trust is important. And we show that the same architecture can be used in the cumulative learning scenario. So multiple phenomena can be realized using the same architecture or variations of the architectures. And of course, as I said at the beginning, we like to match our robot data with empirical child data to make sure our approach is strong. So which directions are we taking at the moment? One is to extend, scale up the system to handle larger repertoires of behaviors, more words, and so on. Another direction is explanatory AI for trust. I mentioned this before. And of course, as I said, it's important to look at the applications. If you get the slides, they will be here reading if you want to follow up on this project. And I'll stop here. And I think, Lorenzo, I will stop the video sharing, screen sharing.
Yeah.
So that you don't see this effect. Okay.
Okay, perfect. Yeah, fantastic. Thanks. Thank you very much, Angelo. Sorry, wait a sec.
So that.
Hi, Angelo. How are you?
Hi, Casper. Good to see you.
Yeah, good to see you too. Thanks for the very nice presentation. Very nice. I have a question about the robot that learns about the different objects from different people. And so my understanding is in the first instance, it was trained by someone it trusts from the beginning for some reason, and then kind of sticks to that. So if someone comes with a different T-shirt and says something different, they are not trustworthy. But could that ever change? Could the robot learn that it got it wrong to start with because the initial person was making a mistake or deliberately deceiving the robot?
That's a very good point. Yes, in the sense the video that we showed was just a test demonstration, but there is nothing that stops us from updating the probability in these Bayesian networks, which actually this should be the case, right? You should also adapt. Also in the video on the with the pepper, when the robot sees for the first time a person, it's mapping its history of trustworthiness in the population, previous population, to the new person. So that's why the robot didn't trust the person, just maybe its experience. We actually in the paper manipulate the amount of relative proportion of trustworthy versus non-trustworthy people you interact with. And we would expect, maybe one-shot learning type approach that if you make a mistake, especially in this case, you should be able to fix this in a faster way than having to repeat all interaction with a new person until you train your system. But we have looked at this relative weight of your experience. So it's an open dynamic model of trust.
Okay, good, thanks. Maybe I ask another question. No one else is asking anything. It's a minor question. You spoke about how to learn how to count and understand the relationship between numbers. I think it's a nice idea to use the fingers. and that can only be done by robots, really, which have fingers. But there was a separation between 4 and 5, which I didn't understand, because I suppose the iCup has 5 fingers. Yeah.
The 4.
Only 4 fingers.
Sorry. So these two are together.
Okay.
So instead of using a standard, even if I did this, we took inspiration from an American Sign Language counting sequence, and we adapted this to make sure that the iCup with 4 fingers could do this. So you said that would there be a difference when you jump from 4 to 8 or 5 to 10? I guess this is 5 to 6, right? This is what you want to say. There is no body continuity, right?
Yeah. I mean, I thought it had 5 fingers, but now I understand why there is a separation between the 4 and the 5. But if it was a 5-fingered robot, I suppose the 5 would be together with the 4, yeah, with the first 4.
So motor control point of view, the iCup has 5 fingers, but the last 2, I don't know if you see the video, are controlled by the same joint. Okay, so it's like you can control 4 fingers. The last 2 are together.
Yeah. But
I would say, regardless of the implementation, in our case, we didn't really do 1, 2, 3. We used 1, 2, 3. I don't remember exactly which combination from Amazing Sign Language. I would say that in this specific case, I think the robot wouldn't really distinguish. If you have a fixed way to do a sequence, what counts is that each motor sequence is next to another one. This next link, one next link, is enough for you to locally maintain the similarity. So even if you go from 5 in a normal 5-finger hand, you go from 5 here to 6 in the other arm. What would matter is that you systematically keep this in the training. Now you make me think that in the actual results, there is an error that the robot makes in the similarity between, I think, 6 and 7 or 5 and 6. We never explained this. I just say in my presentation, even if I can see this, say the sequence correctly, my similarity can still be a bit, fuzzy. Maybe we should look at if the similarity error is actually linked to a sudden shift of motor similarity.
Yeah, because I mean, I think
you are hinting at this.
You spoke about left hand and right hand, so I was thinking that maybe you bring those together, that in one hand, and those who are in the other hand, are separate from that. I don't know. Yeah. Okay.
Yeah. No, I'll go back to Alessandro to have to check where they are. Very, very good point.
Okay. Let me know. Yeah. Let me know. Thank you.
Okay, yeah, by the way, thanks Angelo for the talk. I see more questions coming on the chat. If it's okay for you, if we go a few more minutes?
Yeah, a few more minutes is fine. Maybe if you summarize or read the question.
Yeah, so there is one question about the language learning experiments. How does the robot differentiate between red and cup?
So in this case, if you remember, there are 2 component maps, one for color, one for shape. So you would have the 2 win-at-a-call nodes being active. Then you hear the word, red or cup, and you remember cross-situational learning. You do this tuning of these Hebbian connections over a few repetitions. So at some point, if it's always consistently there, the red and the word red, then you will learn the association. But the representation of shape and color is given by the 2 different component maps in this version of the model.
Okay, thanks. And then there is a question by Elisabetta. I will try to interpret the question. Elisabetta, if it's wrong, just jump in. But the question is whether that in some cases we generalize when we learn a new word, because we know already some other word that is related, but we unconsciously generalized based on the word itself. And the example Elisabetta she's making is in Italian, is the relationship between prato and prateria. So a similar word that but then kind of suggests us a possible meaning.
So if the question is related to, are we using phonetic similarity of words to look at potential semantic similarity?
Yes, I think so.
We haven't looked at this because we have a limited really data set or lexicon. So I couldn't answer what the robot would do on this. I would imagine if you have a richer repertoire of visual categorizations and actions, you would use similarity from the semantic space for sure to enrich the word. How phonetic similarity will be used, I don't know. In our current model, it wouldn't be possible because although we use a cone and map for colors, so two things which are of similar colors will be activated probabilistically closer together so the meaning can overlap. In the representation of the individual words in our map, although it's not really a map, in the one-hot encoding of our words, there is no information about the morphology, prato, prateria, the ending changing, or phonetic similarity. So it wouldn't be possible in this version, but there is no reason why it shouldn't be possible in a follow-up study where you manipulate this property, which you think is important.
Yeah, so if you had a representation of the words that is more related to the sound, for example, that could have been possible, that a similar word will have a similar representation.
Yeah.
Very interesting. I had like a general question related to the beginning of your presentation, or let's say maybe half of it, when you showed those developmental stages the babies go through, and there are these like distinct stages in which you see differences happening in the language. And I was wondering whether those are related also to other developments, for example, motor developments or other type of developments that are crucial.
So definitely, yes, in general. There are parallel developments in motor control and so on, especially in the first stages, of course. Specifically for our approach to language learning and this grounding of words, we assume that phonetically you recognize and segment a word, so this is already finished in terms of development. In reality, this is not the case, especially in the first words where you learn. It's a continuous tuning of the sound of the word, the segmentation of the word, and the meaning. So we assume this is not happening. And again, in motor development, when we look at if you remember the video of the robot performing a series of action, we assume there is a full potential to control your arms and your joints. So in our case, we don't focus on this, but in real world, if you wanted to model a richer set of phenomena, you would have to consider how phonetic, sound perception, sound production, motor control develops with these aspects of language learning, of course, which would
I was curious, for example, if for example, the vocabulary sprout that is it's more or less around a certain number of months of age in all kids. I was curious whether that is like, is that at the beginning of the second year you mentioned?
No, end of the second year.
I would say,
yeah, the hypothesis for the vocabulary spurt, the sudden growth, is not much about the fact that, for example, you can do more things perceptually and motorically. It's more that you have reached a critical mass of your dictionary, and you need to cognitively reorganize this representation internally in a different qualitative way. There are a few hypotheses on this, but I think it's too late in development for it to be affected by, let's say, motor. But having said this, I don't know the exact literature, so maybe some hypotheses might be based on parallel development.
No, but it makes sense because at the end of the second year, a lot of motor capabilities are already quite developed. And maybe a question a bit related to that. I was curious about the experiment of the counting of the objects, and you mentioned that both in the robotic model and in the experiments with children, so the children were better at counting the object when they actually did the motor action. So I was curious about this, let's say, again, motor contribution, and whether that could be related also to the motor system acting as a focuser of attention. So if attentional mechanisms are related to that.
So in the experiment, we manipulate both. I mean, in the last experiment, I don't think we manipulate attention, but in the previous version of the simulated ICAP, we manipulated attention. Attention can be represented where when we had like a one-hot encoding, before we use the deep learning approach, when we have one-hot encoding of the objects, you could actually increase or decrease the intensity of the activation for the specific target object of attention. I would say more than attention in this sense, it would probably be also the fact that you have, your body is redundantly giving you information about the task. Mm-hmm. So it's about counting them, it's attention, and then it's a modulation of your motor resonance almost. In fact, there are effects on the amplitude of the pointing. The same experiment by Alibali Di Russo looks at small variations in pointing versus big variations. So if you do ampler, bigger, if there is a bigger distance between the different points you are pointing at, you enhance your learning. So there must be a real motor contribution beyond attention. Otherwise, it doesn't matter if I point at things which are close to each other, but the pointing allows you to pay attention to the right position. It shouldn't matter if I do this with things which are far or close.
Right. Right. Yeah, that's very interesting. There are a couple of questions I will read from the chat. So one is about NLP. The question says, the learning process you mentioned is based on one hot encoding of word and association relation. How could NLP, natural language processing method, support the learning process? Is it possible to use a pre-trained word embedding instead one hot encoding?
So at this stage, this is a theoretical choice I make. So at this stage of the early discovery of first words, I think using a, let's say, word-to-vec representation wouldn't be good, because word-to-vec representation implies that you're telling already the child or the robot, look, these two words are similar semantically. We are modeling the discovery of this semantic similarity. So it is good that we use this kind of separate one-hot encoding at this stage. Of course, we would expect then there to be a loop back to the representation of words that embeds gradually the similarity in the activation and use of the word.
I see. Thank you. And there is another one related to the theory of mind part, and specifically the Salient experiment. So the question is, could it be that younger kids, when saying that Sally should look into the box rather than into the basket, they actually do not understand the question rather than not perceiving the state of mind of subjects?
I mean, it's a legitimate hypothesis, but psychologists, when they run their experiments, they do think of all the possible alternative explanations. Plus, 3-year-old children, I think, understand well. So a good hypothesis, but I'm sure it has been demonstrated this is not the case. There is another explanation for the choice. It's called the A not B error, which is studied a lot in development. That is, children have a tendency to pay attention to the last event. So because the last event is where they see the object, this is so strong for them that they can't compensate with the representation of the mind. Plus, remember, we say there is not yet a representation of the other person's mind, full representation. In fact, I simplify my results. They do 3 age groups. One age group in the middle gets it better, but not very often. So maybe these are the cases in which you are rearranging your perceptual capability, the representation of mental states, and so on. But I would say definitely not. It's about not being able to represent the mental states of another person.
Mm-hmm. So yeah, I mean, maybe another one I wanted to ask is again related to this, let's say, motor contribution to perception, and this comes also in your experiment with the learning of the words that are where the objects are positioned in different locations. So you mentioned that then with your robotic model that is informed by the robot posture, you were able to predict the result of a new experiment in which the object was also put like up and down with respect to the robot. Would it be similar if, so I was wondering what happened if the experiment with the children, if when they ask the children the name of the object, they will ask the children to come to the opposite side of the table, so that
I mean, a manipulation where you distract. I mean, I don't know the details of all the possible counter experiments that they did, but I think for their explanation, for their theoretical explanation, it's enough to show that the swapping of location is, and therefore the swapping of your postural changes is enough to disrupt this.
So, but yes, basically the idea is that it's related to the posture, right? So if the kid is not the absolute position of the object in the table.
No, it's the posture. The paper and the theory is about the posture. And the model implementation is a representation of posture, not of position. There is no distance of objects in the model or in the children explanation of their behavior.
Mm-hmm. And based on your, let's say, discussions with the psychologists on this, they agree that this could be a relevant factor, right? That
yeah. Actually, it's title of the papers, and these are postural. Remember, it's not passive vision. It's active interaction with the environment through body posture. Yeah, they manipulate the posture. Yeah. And we also manipulated in the top down. We manipulated the posture. It's like the robot is standing or sitting. In a baby, is the parent who is holding the baby that stands up or sits at the table.
Okay. Yeah, I don't see any more questions. Actually, okay, yeah, maybe actually there is a question now. So I will read with the experiment where the child was learning what objects are called. It was assuming that people are knowledgeable, but maybe untrustworthy. Presumably, as children get older, they learn that parents are trustworthy, but not always knowledgeable. Can we model this?
That's very refined.
Or some teachers are not knowledgeable.
It's a very good point. A nice idea for a further up study, of course. It's a balance of competence and trust, the link between trust and competence. As you know, guys, trust is a hot topic in funding, trust and human interaction. So this might be an area for development.
So ideally, I think, yes, that could also be modeled in terms of a probabilistic relationship, probably, as an additional variable. I think it's nice that you presented this study in the paper, Massimo, and you did it's a Bayesian network models, because also my students have learned a bit about Bayesian networks and how to use them for more. So we recommend also to read the paper in more details. It should be quite interesting for them. Maybe just a quick one. I was actually showing some of your video already in some of my lectures, and so we quickly discussed a few of these things. And one question during one of my lecture was what happens when kids are in this period where they always ask why this, why that. So when that happens, and what is the process? I don't know if you had a comment.
I don't know the answer. It's a stage where this happens. Yeah. I don't remember even the age, but we need to ask the psychologist.
Okay. All right. Yeah, I think I don't see any more questions. I think it was very, very interesting and very informative for everybody. Yeah, thank you so much.
Thank you, Lorenzo.
Thanks a lot, Angelo. Good to see you.
Thank you. Keep in touch.